Hello, hi everyone. I'm Sufian here from University Sultan Zana Abidin, Terengganu. So I'm happy to present my study, doped plastic scintillator properties for soft tissue dosimetry. This is the outline of my presentation. The first one will be the introduction, and second is light output spectra of plastic scintillator. Third is composition for underestimation of tissue dose by plastic scintillator, and fourth will be conclusion. So, in workplace with radiation generating device and radioisotope such as an accelerator, X-ray tube, and radioactive nuclei, radiation dose must be controlled properly to prevent hazards caused by exposure to radiation. So absorbed dose in the unit of Gray is the physical quantity related to dose, and the absorbed dose it is defined as the absorbed energy within the unit of weight. In other words, the absorbed dose could be determined directly from the absorbed energy inside the plastic scintillator. And as we know, the value of absorbed dose is related to the photon interactions and the material. For medical dosimetry, the dose to tissue is often the quantity of interest. So then we can see that tissue equivalent material is preferable to create dosimeters that directly represent the absorbed dose on human soft tissue. The use of small size air ion chamber is possible with main limitation, low efficiency due to the low density of air. Uh, For example, in the medical field, plastic scintillator is successfully applied for photon dose measurement on radiotherapy in the MEV energy region, or for depth dose measurement in phantom that require real-time monitoring dose in a small volume, because again, plastic is a water equivalent material. And we can see here there are several good properties of plastic scintillators, such as have a higher detection efficiency, soft tissue equivalent, lower cost, flexibility in shape, and independent of atmospheric factors. So the question is, does a single standard plastic scintillator is suitable for absorbed measurement from low to a high energy photon? So several studies have reported that the decreasing light output, or we can say decreasing of electron response, distort its response for incident photon energy below a few hundred of keV. So this is an effect known as ionization quenching. So this is the problem of plastic scintillator for absorbed dose measurement in keV region. And many studies concerning absorbed dose either through experiment or calculation without considering the degradation of this effect. So this is an example of the figure showing the ionization quenching effect, which is from our last year publication in the Journal of Applied and Radiation Isotope. So this figure show the relative electron response of the EJ200. So this is a standard plastic scintillator where we measure the electron response with quantum coincidence technique. So we can see that from this figure, the response or the relative light output of plastic scintillator will decrease significantly below about 150 keV. So therefore, a standard plastic scintillator should show significant underestimate of absorbed dose to soft tissue for low energy sources. So the approach of our current study, in order to improve low energy photon dosimetry by using plastic scintillator, so at first we will do experiment and also Monte Carlo simulation for pulse height distribution with considering a quenching effect in our EGS5 code. And then from the absorbed energy, we can obtain the measured and also calculated absorbed dose. And third, we will calculate for composition of underestimation for soft tissue dose. Comparison of pass height distribution between measurement and calculation is very important for us to understand phenomena inside scintillator. So in this case, we will use AGS5 Monte Carlo code and apply the previous shown measured quenching effect to the deposit energy. So it is in this study is quite straightforward. We will use two sources, americium 241, where we know it has a peak energy at 59.5 keV, and also a higher energy source, manganese 55. It has a peak at 834 keV. So here is the measured and calculated pass height spectra, the overlap plot of both for EJ200 for standard plastic scintillator and also EJ256 for 0.5% lead doped plastic scintillator. So A is for americium 241 and B is for manganese 54 source. So by considering the quenching effect, the calculation could reproduce the experimental data well. Okay. And the effect of lead doping on the pass height spectra can be seen in the figure for both low and high energy sources. So as we can see here, the effect is more significant in the case of americium 241 for lead doping plastic scintillator, as indicated by the circle dotted data and also the histogram of in the red color, while the effect of lead doping in for higher energy gamma sources is not so it's not significant. The lead doped improve the detection efficiency and energy absorption with higher pass height in comparison to standard plastic scintillator. While in the case of manganese 54 source, both the measured and calculated results agree that there is no significant contribution of the lead doping on the pass height spectra. So next, the agreement we could discuss from the viewpoint of absorbed dose. In order to obtain the absorbed dose from the previous shown pass height spectra, we need to calculate by using the equation number 1. To obtain the absorbed dose, we are summing up the absorbed energy deposited in the scintillator from the pass height distribution spectra, and then we divide the absorbed energy to its mass and to yield the output in the unit of MeV per gram. Then we can convert the energy per gram to in the unit of Gray, which is the physical unit for absorbed dose, by using following conversion. So this slide shows the data of absorbed dose in the unit of microgray per hour from the previous pass height spectra. We have two tables here. Table 1 is belong to EJ200 for standard plastic scintillator, while table 2 is belong to lead doped plastic scintillator. And the M is for measured data, while C is for calculated data of absorbed dose rate. So at first, when we look at the absorbed dose rate value for EJ200 and EJ256 from manganese 54 sources, we can see there is no significant difference in terms of absorbed dose rate value. While in the case of americium sources, there is a significant effect of lead doping for lower gamma sources of americium 241. The ratio of absorbed dose in EJ256 to the EJ200 is about 3.6. So we can say that adding lead of 0.5% of the total plastic scintillator weight significantly increase the photoelectric absorption of low energy gamma photon with a lower effect on higher energy sources, so that we could suggest doped scintillators to compensate the decrease of response at low energy photon in comparison with human soft tissue. So this figure shows the feasibility of lead-doped scintillator to compensate the underestimation of tissue dose by standard plastic scintillator, particularly in the low energy photon region. On the y-axis, we have the ratio of calculated absorbed dose in between absorbed dose within the scintillator to the absorbed dose in soft tissue of the same size as a function of incident photon energy. So standard plastic scintillator represented by the black dotted data show significant underestimate of absorbed dose to soft tissue for low energy below 200 keV. So this is expected since the effective atomic number of plastic scintillator is lower than that of soft tissue and the low electron response of at low energy region as previously we discussed. Lead-doped with 0.5% offer a good candidate to overcome the underestimate of soft tissue dose for dosimetry application. The 0.5% of the lead-doped plastic scintillator is evident for soft tissue equivalent, making it ideal for low energy photon dosimetry as shown in this figure. So the absorbed dose value closer to soft tissue in a wide energy range. As a conclusion, comparison of pulse-height spectra between measurement and calculation is very important in order to understand the phenomena inside detector. We successfully performed the comparison in absolute basis for various gamma sources to obtain absorbed dose. The study shows that the calculation results are in consistent agreement with corresponding experimental data of both scintillator EJ200 and EJ256. And the lead-doped scintillators compensate for the underestimation of soft tissue absorbed dose from standard plastic scintillators. From this point, the property of the plastic scintillator becomes clear when used as a dosimeter for low energy photon, as the nature of plastic scintillator was studied only in current mode. When used as a low energy photon dosimeter, so this is a significant improvement. And finally, the performance of lead-loaded scintillators was shown to be better for soft tissue photon dosimetry, particularly in the low energy region. And calculation with EGS5 code can be used for dosimetry study of plastic scintillator by considering both the deposit energy and light output. So with that, thank you very much for your attention. Bye.